yes, I picked a lovely shade of orange for my first slide. But yeah, so tips to make programming your game less hellish. So this is a really big topic, and I thought a lot about what this talk is trying to do. I transitioned, for context about me, I transitioned away from business software development into making games about 4 years ago, and I spent about 6 years in kind of traditional software development. And so a big chunk of my career was spent maintaining software that, as long as it has customers, will need maintaining. I then taught myself Unity and am now moving over to Godot and have been working solo and in an indie team on various projects. And a problem I didn't understand when I started making games was why I was so slow to make games. Like, I'm not a rock star developer, but I felt like I was a pretty good programmer. And so in this talk, I kind of wanted to go back to the basics, look at the programming advice I learned over my career, use what I've learned in the past 4 years to kind of articulate where it applies when making games, and to kind of come up or agree on principles that kind of ground these rules. So as such, I'm aiming this at programmers who are earlier in their career or people who come from other disciplines. For those in the audience who are more experienced programmers, it probably will be more of a refresher, but I hope I managed to present it in a way that's still enjoyable. So good place to start is, what is bad code? And there are a lot of things that we could talk about when talking about bad code. There's performance, or whether it's buggy, doesn't work, brittle. And for the purpose of this talk, I'm only going to talk about 2 aspects, because I think they're the most interesting, because they're the ones that follow you across your career. And this is code that is hard to understand and code that is hard to change. And this is kind of judgmental. So like, I'll rewrite this. It's hard to write code that you can understand, and it is hard to write code that you can change. And this is your aim as a developer. So we'll start on the first one. It's hard to write code that you can understand. And let's zoom out a bit. What does it even mean? What is code? What does it even matter anymore now that we have AI? And I really like this quote. It's from Clean Code. And it says, "We will never be rid of code because code represents the details of the requirements. At some level, those details cannot be ignored or abstracted. They have to be specified. And specifying requirements in such detail that a machine can execute them is programming. Such a specification is code." So this was written in 2009, but it feels very appropriate today with the rise of AI coding tooling. For years, we've been talking about generating code so that anyone can program. And I think this reasoning is very insightful, because I think it gets to the heart of the difficulty with coding. There is a level of detail that is unavoidable. When you use a tool like Unity, it doesn't raise the level of detail, it writes large swathes of code for you. Did they build the thing that you need or not? Is there a component that already fulfills your needs? But the precision doesn't change. The computer will do exactly what you tell it to, even if you don't yet know what it should do to make your game fun. You don't get to be hand-wavy or vague when you program. You have to make decisions so that your intent is unambiguous. And so, disclaimer, I don't use AI when coding, so my opinion is completely unjustified. But I think even if we do end up interfacing with AI in order to code, we will still need to be able to instruct the AI with enough precision that the AI will generate the code we need. As our problems become more specific to our code base, we need to instruct with more precision. Understanding our increasingly specific problems well enough in order to generate code that solves it is still coding. So when we program games, we're operating across 2 levels of detail: the high-level product-focused version of what the moment-to-moment gameplay is, and the high-precision, detailed, unambiguous instructions. And I think this captures the scale of the problem. I hypothesize that it is very easy to create a code base that can't fit in your head because of having to operate at this level of precision. So you have a limited amount of working short-term memory. And since you can't fit a code base in your head, then the best you can do is to alternate between like a high-level kind of understanding of the code base of this class interacts with this class, and that's because this roughly does this, and then the specific details of the part of your code that is relevant to your problem right now. And the metaphor I'd like to use is that going through a code base, particularly a new code base, is like traveling through a mansion with a torch. You can only see a certain amount at any one time under the torchlight. The torchlight represents your short-term memory, working memory, and what you can see is what your understanding of the details of the code base that you're working on is. And so with this, I'd like to propose a new definition for good readable code. And that is, good code leaves your working memory free to solve your problem. You can't make a game in a day, and so you need to aggregate your work over time. Your job as a programmer is to handle this snowballing complexity. The code you wrote yesterday should help you solve your problem today, and the code you write today should help you solve your problem tomorrow. And so as time goes on, and you've written a wealth of functionality to help you build your game, it should become clear that your code's readability is really important, because how else will you leverage all that work that you've done over the last week, month, year, years? So code is read much more often than it is written. And a lot of intuitive optimizations increase the speed of producing code, but actually the bottleneck in coding is your comprehension of the code that's already there. And again, you have a limited amount of working memory. You don't want to relearn how you implemented a function yesterday to use it today. It's read a lot more. And so your aim, ideally, is you should know how to use your function from just the function signature, from the name and parameters alone. You shouldn't need, if you don't need to change that function, you shouldn't need to look inside. And just for clarity, because not everyone here uses Godot, but this is the syntax that I'll try and generally use over the course of this presentation. It's like a function parameter signature for Godot, which starts with func, and then the function name, the parameter, and then the type is after the parameter name, and the return type of the function is right at the end of the function signature. So let's look at an example. So I look at this lovely function called getThem. I have no idea what this does. The name isn't helpful. I don't have a return type. In Godot, unfortunately, it's optional to state the return type. So the fact that it doesn't show one doesn't indicate that there isn't one. So I have to inspect the function to even see if this returns. It probably does return because of the get, but I don't know what. So we can look a bit further in. So it seems to return some sort of array, and it's going through the items in the list. And based on this condition, if the first element of the element is O, then it adds that to the array that will then be returned. So again, there's a lot of questions here. I guess, like, what is the list? We also have this return type of an array. It probably matches the type of the list, but we still don't really have more information about what this is, besides, I guess it contains a string. We also don't know why 0 and O are special on this line 4. We don't really know the meaning of this kind of check. And we don't really know what to do with this. So if this was a code base that I was working in, I would probably have to inspect a few more functions to kind of see how these are handled in order to work out what the contents are. And so now I'll tell you that that the list is a game of life board, and that this is code to show game of life. Game of life, if you don't know it, is you have every cell on a board is dead or alive, and every turn there are rules to dictate whether the next turn the cells are dead or alive. So here's some renaming that we could do to make this function a bit more clear. So we could rename the function to actually give us more information. So get alive cells makes a lot more sense in this context, as well as be more explicit with the return type. Unfortunately, this is about as explicit in Godot that we can get with nested arrays. I don't think you can go any further to say what the nested array contains, but it's still a bit better. And then the check, I've added meanings to the O and the 0 to make it more clear what this check is doing, which it seems to be a check on whether it's alive based on also the name of the function. But we can do better than that, because this is still doesn't quite answer the question, what do I do with this? And so what we can do is we can wrap that nested array in a class to give that data meaning. So I have this cell class, and instead of this equality check that I have to kind of infer what's happening, I can give it a name, and I don't then need to know, like, it has meaning, and I don't need to know anything about the implementation to know how to use it. If cell is alive, add it to the array. That's a lot easier to read. And also that helps me with then, what do I do with the return type? I have an array of cells. My IDE, if I have a var cell, a variable cell, and I type dot, my IDE will autocomplete for all the functions and methods that are available to me. I have a lot more information about what to do with this return type as a result. And then finally, we can just look at the function signature to go back to our original criteria. Given this function signature, do I need to look at the implementation to know how to use it? No, not anymore. I can just use this. So next, I want to talk about kind of patterns that you can use to help yourself out. So the following are words that are frequently used in function names. Can you work out which one is the odd one out? I'm told that there is a big lag in the YouTube comments, so I can't make this as kind of interactive as I'd hoped, but I will give you a little bit of time to work it out. For those of you who maybe haven't seen this before, get normally returns, you normally say get to get a field from a class or get like some specific data from a class. Set normally overwrites that data. Is some kind of check on a, it's hard to, as an example, like if I have a door class, is locked would be like a very sensible method to check if the door is locked. And then has might be to check that there's an element in some sort of collection. So the odd one out here would be set. And there's a few ways that you could have come to this conclusion. It is the only one that doesn't have a return type or wouldn't necessarily be expected to have a return type. Is and has both return booleans or true and false, and get would return anything. But set is normally an overriding, and so you don't normally have a reason to return. But the other side, you could say it's the only one that's expected to mutate state. It's the only one that explicitly says that it will override some data or save kind of the data that you pass in some way, while the other ones don't have that expectation associated with them. So this makes sense. If you have a function that returns void, it must be, and we're talking kind of outside of these names now, but if we just look at the return values, if a function returns void, it returns nothing. It must be mutating state, because why else would you call it? And similarly, if you're returning something, it can be hard to write a function name that articulates the reason that you want to get this data and also that you're mutating something. It becomes like a bit long. And there's a principle called command query separation that says that this kind of pattern of your return values and like the mutation of state should be this everywhere, not just for kind of these names where this behavior is more expected, but you should never, if you return a value, you should never mutate state. And all your functions that mutate state should only return void. So the term command query separation, and here's some more examples of how you'd use these if you've not seen these before. So command query separation was devised by Bertrand Meyer, I didn't check how you pronounce this, as part of his work on the Eiffel programming language. So he calls them commands, the functions that mutate state, and queries, the ones that return data, and that no method should do both. And by doing this, we should better communicate intent. So let's have a look at another example. So I have this function, if set username Caroline. Now set generally suggests that I'm mutating state, but I'm also returning a value. And it's very unclear what this function is doing. Maybe it sets the username and then returns true or false depending on if it succeeded. Or maybe it tells you if the username is already set to Caroline and it's more like a query and the set is like a weird naming choice. And if we now follow command query separation and we write it more like this, if the username exists, then we override the username. This is much easier to read. This isn't a super like dogmatic religious principle. There are many common exceptions to this. I've listed helpfully one from Godot and one from Unity. But this idea of like a pop function, which I think is normally associated with queues, but you find them on the array class, this idea that you both mutate an array by removing an element from it and then return that element. Or in Unity, you add a component and you also return that component. They are useful functions. So yes, it's kind of more of like a rule of thumb than like a super religious principle. I would add, if you do violate command query separation, I would low-key advise that your function looks more like a command than a query, and that it clearly says that by calling it your mutating state with some reason to return that value, then silently mutating state in a function that looks like a query. And then here's an example that came up in my code. I have a plant class and I want to next step, or the next turn I want to grow that plant. And I decided that I wanted to change it so that the user would get some information about what would happen the next turn without actually committing to that. So it became like a predict next step with a return value. The problem is I left this self increase age, which is very clearly a command. And it caused a lot of bugs before I realized what I'd done. And I made a quick fix of like making a deep copy of the plant that I was working off, then calculating the next step and working out what the return value should be so that it was isolated. This is not like good code, but there are ways that you can kind of isolate your kind of bad code into like at least one function so that you can tidy it up later, I guess is what I'm trying to say. There's a lot more I could say about this, but since time is of the essence, I will move on to it is hard to write code that you can change. Obviously, part of this is linked to it's hard to write code that you can understand. You have to understand your code in order to be able to change it. But I also want to talk more about, I want to build on that idea. So, and I want to pose a question. So do you know your game works when a new person has joined your team and is working on your code base, when you port to a new platform, when you add a new feature or make changes to your code? I think the first one is quite pertinent because often there's a kind of mindset that if we're running out of time and we have some spare cash, we can just hire a load of developers to speed up development. The problem is, of course, that people can step on each other's toes. You have a bunch of new developers on a code base. They can create a lot of bugs kind of by accident that then you need to delegate that fixing to someone, and that's going to take up a lot of time. So being able to easily onboard people is generally really desired because it's really important it's really important at the point where you hire a lot of people. Your deadlines are becoming really urgent. With the last one, when you add a new feature or make changes to the code, I would pose a further kind of hypothetical scenario. So imagine you have a showcase in an hour. You've just spent all night fixing bugs and you need to decide which build to showcase. You know the press are going to be at the stall this morning, so it has to be good. Do you pick an old build with some really annoying bugs, but which aren't game-breaking, or a new build that you haven't yet had time to test, but has like a cool new feature that you would like to show? It would be really nice to be confident that your new build doesn't have a game-breaking bug in it. And the problem, so this is a quote from a book called Working Effectively with Legacy Code. And the author, Michael Feathers, says that the default for everyone coding, or the default for most programmers, is the edit and pray method. When you use edit and pray, you carefully plan the changes you're going to make. You make sure you understand the code you're going to modify, and then you start to make the changes. When you're done, you run the system to see if the change was enabled, and then you poke around further to make sure that you didn't break anything. The poking around is essential. And when you make your changes, you're hoping and praying that you'll get them right, and you take the extra time when you're done to make sure that you did. And during the book, he makes a lot of cases of ways to fix this, or to kind of lower this QA time, because this extra time that you take for poking around is both time inefficient, but also not that effective. Like a lot of that is a very leaky net that a lot of things can evade you through. So continuing the scenario, imagine the following. You picked your new build to show at the showcase, and you watch someone playing. On exiting the third level, the game shows a blank screen. What the hell happened? You check your code base and replay it. At the end of the third level, you see an exception, level load exception, cannot find level -4. You double check your files, and it turns out it's called level_4. Some bastard put in the wrong string in that function. And these types of exceptions are the worst because they're so time consuming to find. So my whole framing for this section of the talk is about feedback loops. If I push a bug, and in this case, it's if I push a bug to the game, how quickly can I discover the bug? Because the sooner I find that bug, I mean, the less the impact, the less likely it's going to be to bite me later. The quicker it is to locate the source of that bug also, because there's fewer lines of code from when it was created to when I discover it. And then also the fresher that changes in your memory, so the easier it is to understand the code and fix the problem. And generally QA is just really expensive in a small team. Like if your team is spending a lot of time testing, that's time that they could otherwise be spending developing the game. So you really want to discover errors as quickly as possible. And not all errors are created equal. The best kind of errors are those with the shortest feedback loops. So compiler errors are the best. So a compiler error is amazing because you cannot build your game without knowing that you've got an error, and you know instantly where the error is because the compiler tells you where it is and what the problem is. So you want to, if possible, that would be, if all your errors in your game were compiler errors, that would be the best scenario. And the kind of solution then I would propose to the level loading problem would be some sort of map from enums to strings. The idea that any developer on your team would have to remember the name of a string in order to load the next level is just very error prone, because most strings will run this, create this like terrible exception. And if you restrict it, you only need to check it once, and then you have confidence that everywhere else that you call this function with these types, that nothing will go wrong. You could also use a constants file, that's also okay. But the problem with a constants file is in the Unity editor, I think you'll still have to use a string. And if you use an enum, you get a nice drop-down list. So like wherever you call this function or use this data, if you have an enum, it's just guaranteed to always be work. You can have full confidence. The next best would be fail fast errors. And what I mean by this is that you can compile your build and that will work. But if you play your game, you'll discover really quickly that your game's wrong. Like the first 5 seconds or something, there's some sort of check there that kind of screams if it fails the check. And so again, it's you can build your build and then play it and just check that have those checks run. And maybe an example I'd use here is like if you have some configuration, like some sort of JSON you need to load, you might want to do some checks that it has all the data expected and there's no missing fields. Maybe like a check on your save data if you have any, particularly if the format of your save data changes over different versions of your game. Yeah. And I have to mention automated testing. If I go back to that quote with the edit and pray that Michael Feathers wrote, his whole book is basically how automated testing is the solution to edit and pray, the only solution. But it's a tool to shorten your feedback loops. The smoke test in the last slide, I would argue, was a type of test. It is a bit of code you write to check that your code works. And so, yeah, tests are generally pieces of code that error very loudly when something in your code isn't working as it should, or when the behavior has changed. In the screenshot here, I have a series of passing tests. If any of them were failing, there would be a little X. And if I click on the test, it would give me more information about why it failed. And I can configure that to be as informative as I want. And so you can see the trade-off here is if the behavior of your code is changing a lot, then your tests will need a lot of updating. Automated testing really shines in the later bits of development where you have a lot of code with behavior that you want to preserve. So you have like a change you need to make and a lot of features that you know it could affect. And your tests will then tell you if the changes you made affected the features that you want to preserve. That is where it really shines because it shortens that feedback loop. Automated tests should run in seconds, ideally, while playtesting the game for like, if each of these is something I need to look out for, I mean, optimistically, let's say it takes 5 seconds per test. It's still like a lot of time every time I want to run through this suite, and I might have to run through the suite multiple times in developing a feature. And we can also consider this feedback loop in development. So I didn't really specify when you would write these tests. You could write these tests after you've created the feature. They still have quite a lot of value, particularly if in the future you think there's a risk that some code could change that feature inadvertently. But you could also write them before you've created that feature. It would fail because the feature's not implemented, but then I have a short feedback loop by which to check if I implemented the feature, plus all the tests that I would have from other features. And I've done this, so there's a feature that I did for Queen's Guard. So we made this game, Castle of Glass, and there's this ivy that spreads. And this was really difficult. I didn't really have a good way to solve this, and I kind of struggled in writing this code. And there's a lot of different scenarios. Like I've given on the right, it's only 3, but I've in reality, I've got like 20 kind of different geometries that this ivy could crawl over, and different ones would give different bugs at different times. And so the test suite that I showed earlier was the test suite to check that that worked. Every time I found an edge case, I would add a test suite and then make changes and check that the old ones hadn't broken. And if the old ones had broken, then like do some more changes. And I never needed to change this code. Once this feature was done, which was done in about a week to 2 weeks, like kind of part-time. And then I never needed to change this because we'd already decided the functionality was required as part of this game. But it still, I think, massively reduced both the time of development and kind of my confidence in it working then and now. So I'm now going to go kind of off programming a bit and more reflect back on what I started with about being a developer that's starting to make games and like, why is it taking me so long to make games? It's not prescriptive advice. It's more like my current view on what an idealistic scenario to make games would look like that would make life easier. So one mistake that I made in my games was to over-engineer them before I had validated they were fun. I thought I could build my way to a good game. And if it changed direction during development, I could adjust with my coding skills. But I think that was very naive because it's hard to write code you can change. I was just making my life harder. If I had known what I was building, I wouldn't need to write code that needed to change so much. Like, I think it's significantly easier to write code that doesn't change. Like it is. Oh, interesting. That doesn't show. But yeah, it's like orders of magnitude easier to write code that doesn't change. The hard bit about writing code is writing code that changes. And so to any kind of I don't know much about game design, or I'm like I want to know more about game design, but I'm not an expert on game design. But my advice to people who maybe sympathize with the situation that I described about myself is be very don't get attached to your prototypes because your brain is a dirty, sneaky liar about what's fun. As a creative endeavor, you generally try and make stuff that's different to what already exists. But if it's different, you don't know if it will work. Fun is not intuitive, and it can take a long time to find. And a consequence is that your attempts to find fun will contain a lot of scars of half-built features that you don't need, workarounds, imported assets for something that you actually need to rebuild from scratch. Like starting with a rigid body for a platformer is a classic example. I think everyone generally writes their own. And so the earlier you can identify the fun bits, the more you can start your code base with a clear idea of your game, and the easier your life will be. And so the idealized roadmap is that you have this pre-production stage where you're just making a lot of dirty prototypes, and code quality is not such an issue because code quality matters when you aggregate code over time. And if all your experiments are kind of small enough just to validate ideas for you as a designer to kind of understand if they're fun, then it's a lot of the rules like don't apply as much. And at the end of pre-production, you say, I have identified what mechanics I need to build my fun idea. I confirm other people find my idea fun, and I have evidence that people would buy my fun idea. And then you throw that away and you start production knowing exactly what you need to build. And this is like, this is like dream world. This is like, as a programmer, production is much, much easier as a result. And I will defend this with examples. So I talked about Castle of Glass before. This was a 6-month puzzle game that we made as part of the Cartomancy Anthology bundle, which was a game of about 23 games based on tarot, made in 6 months. And part of the reason that we made it within the time frame is a game designer made all the levels in Tabletop Simulator, play tested them by screen sharing with friends, and like basically telling them kind of what the rules were, and then getting them to tell him where to move the player and watching if they would solve the puzzles or not. And so when I had this, I knew exactly what to build. Inkle had this, they made Overboard in 100 days, and they used their decade of experience with making their previous games to, I think they made the script in something like 2 weeks for the game. And the rest of the time was like fleshing out the options, creating the artwork, and spending time eliminating some of the harmful stereotypes they used, which is a really interesting talk. And finally, I want to reference, I watched a lot of the developing series for Game Maker's Toolkit. So Mark Brown, after he's making a game, a Magnet platformer game, and he had this 30-day challenge of making a bunch of levels, and he got a lot of feedback. And then he threw it away and he started again because he said that like that code base was kind of an experimentation to work out what he actually wanted to build. He spent a lot of time then making in-editor tooling and making a better kind of character controller. And to test out his tooling, he made levels. And in doing so, he says, did I accidentally make a video game? Because he'd made it so easy to build levels that he'd made another demo. And I thought it was really cool when I watched this because he threw away a game that, or he started again at a point where I would not have. I think I would have kept it. I think all my intuition was like, that's really late to throw it away, but maybe not. And I want to reiterate, this is very much like an idealized, what I think an idealized game dev journey would be, because there are lots of factors that obviously play into the decision about when to enter production, of which funding is a non-trivial one. I think the games industry is a weird one where you can have an idea for a single player game, go to a publisher and come out with a multiplayer, committing to a multiplayer game. And like I wouldn't do that, but I wouldn't suggest anyone does that. But I also like these things are a bit out of our control sometimes. Yeah. So we always want to make new things. And if we made the same game twice, you would make it completely differently the second time round because you would know exactly what you need the second time round. So I want to leave with this thought of your code base is both your game and your journey to making that game. I also want to add, I think this is why there are designers who learn to code later, I think are really interesting to work with because I think they generally have a better sense of what to make. And so that kind of means you have a much easier life in that circumstance. So any designers watching, I don't know, I think you'll be magic if you learn to code. And and I want to plug, this looks really bad at this size, but I should have picked a higher resolution image. But there's a game I'm working on with Queensguard. So we made Castle of Glass, and this is our sequel. I'm going to cheekily plug this game called Shards Between Us. It's available to wishlist on Steam. I would really appreciate any wishlists. And that's the talk. I am well under time. But are there any questions?
Thank you, Caroline. Thank you so much. Wonderful talk. I've left a message in the chat to ask for any additional questions. You caused a lot of discussion.
Did I? Oh, wonderful.
Lots of discussion, yes. Turns out people love discussing programming things. Who would have thought it? Also, I noted that Robert Ackley in the chat also said, I played that game at GDC the other week. I don't know whether that was referring to Castle of Glass or Shards Between Us, maybe?
I mean, we did have a small thing opposite the main hall. We had like a small table, so it is very possible.
Nice.
I hope you liked it.
Seems like it. Shards. Oh yeah, so Roberts just said, yeah, Shards Between Us, and said I enjoyed it. Nice.
Oh, thank you so much.
Yeah. Getting some applause in the chat. Lots of people saying good things. Nice talk. Brought up some interesting topics to discuss. That's nice. That's why there was so much discussion. Thank you so much again, Caroline, for joining us.
Thank you for having me.
There's many more thanks coming in right now. Lots of applause coming in. Love the talk. Love the analogies. There we go. Wonderful. Okay, see you all soon. Thank you once again, Caroline.